Well, this is video part two. We are now going to go over chemical reactions versus physical changes. Right here, this is a broken egg. This is a fried egg. When I break an egg, there is no smell. There is no new substance. There is no new color. There is no heating up. There is no gas or bubbles. Over here, when I fry an egg, you'll notice that this clear part turns into a white part. That is a color change. When I go over and I fry an egg, if you remember, there is a smell. There can be a gas. This right here is a chemical change. You need to remember that if there are gas or bubbles, that is an indicator of a chemical change. Does that happen when I fry an egg? Not really. But there definitely is a color change. There is a smell. There's a gas. And yes, there is a new substance. The proteins rearrange. This is what the Statue of Liberty looked like when it was given to the United States. This is what it looks like now. What's a big change? Yeah, you've probably noticed that it's the color. To recap, indicators of a chemical change, indicators of a chemical reaction are smell. Another word they use is odor. Then we have gas or bubbles, light or heat given off. There is a very small amount of heat given off of the Statue of Liberty. The way, if I was to see this on the end of level test, I would suspect that there would be a graph and it would show you that the temperature had changed. Remember that if the temperature changes and there's other indicators, it's a very good indication that it is a chemical reaction. Okay. Finally, you'd say a new substance. Okay, so that was chemical reactions right there. This is going to be an increase in heat energy. And how does that impact matter? Well, we remember that this is a solid. It vibrates in place. This is a liquid. And this one is a gas. Remember, as we increase the temperature, as we increase the amount of heat, the particles move around more. So we could go through and make a graph. This could say something like heat energy. This could be particle movement. And it would be a linear graph. It would go up like that. Okay. That's, you've learned stuff like that in fifth and sixth grade. Let's go over this one right here. Which is bigger, 1/1 or 1/100 or 1/1,000? If you guess 1/1, you are correct. 1/1,000 is a very small number. What I need you to remember is this cause and effect statement, and I'm going to shift to blue. As volume goes up, density goes down. Well, that's the whole concept of a hot air balloon. If I heat up particles, fire heats up air. If I heat up these particles, they are going to expand. Expansion looks like this. You start out with a very small cube, and then you end up with a very big cube. These particles are expanding. And as the particles expand, the volume, I might start talking louder, I get excited about this. The volume goes up. If the volume goes up, the density goes down. And this is why hot air balloons fly. If I heat something up, the particles are going to float. That's why we have This whole concept is called convection, where hot things rise. This is why we have hot air balloons. This is why we have plate tectonics. I know that you guys had Mr. Vanoy and Miss Hardy, and you learned about divergent. Well, the reason why we have divergent is because we go through and we have all of this heat in the mantle, and the particles rise, and then they get cold. And when they get cold, they sink back down. And when they sink back down, that's because they're becoming more like this guy. They're having very small volume. When the volume goes down. If the volume goes down, the density goes up and they sink. So we can say it like this. As heat goes up, particle spacing or volume goes up. If particle spacing or volume goes up, objects become less dense and they float. That is how hot air balloons work. That is the whole concept of density. I strongly suggest that you study this out. It has to deal with particle movement. Heat things up, they expand. Heat things up, they move around more. If they move around more, they have higher volume. If the volume goes up, there is less density. I am going to do one more part. The similar concept is going to be heat transfer. If I go through and I look at this graph, if I look at this, which material was able to trap the heat more? Well, it's not the leather. The leather does a pretty bad job. It loses it loses 26 degrees. Fur only loses 10 degrees. So if I was to go through and I was going to try and make myself a coat or a way to keep myself from getting cold, I would want to use a fur coat because it's a better insulator, or it's a better insulator. Insulation keeps heat from being transferred. There will be another video, and that will be part 3. Thank you.